All right, students. The topic of today's discussion is axiomatic system. In the last class, we learned about a natural deduction system and truth table method for inferencing new statements from the existing sentences or statements using different laws, equivalent laws, and a truth table method, new facts can be new statements can be determined from the facts, and NDS is a natural deduction system. Actually, this these things comes under propositional logic, in which we have four methods for proof and deductions: natural deduction system, axiomatic system, semantic tableau method, resolution repetition method. And natural deduction system, there were rules: introducing and introducing or eliminating or, introducing implies, eliminating implies, introducing equivalence, eliminating equivalence, introducing not, eliminating not. These are the rules in NDS. And this example was discussed in order to deduce A and B from A and B or C. And this one, by the application of different rules, we could actually we are deducing A and B or C from A and B. From A, and we start with A and B, and our rules are applied. Finally, we obtain this, and we can prove that it is proved that this A and B or C expression can be proved from A and B. It is another example we discussed, in which this proved the theorem to infer this A implies B and B implies C. Whole expression implies A implies C. This also was resolved this also was proved, in fact, through those rules of NDS. Now, in today's class, we will learn axiomatic system. Axiomatic system is based on the set of three axioms and one rule of deduction. Earlier system had different rules, perhaps 10 rules. Here we have got three axioms and one rule of deduction. And what are they? Well, here A and B is logically equivalent to whole not A or not B, which is logically equivalent to whole not A implies B not or not B. This is first axiom. Second axiom, actually wait, these are not axioms. Axioms are here. These are the equivalent statements. A and B is equivalent to this one, which is further equivalent to this one. A or B is equivalent to not A implies B. A equivalent B is logically equivalent to A implies B and B implies A, which is logically equivalent to not A implies B implies not B implies A. So these are equivalent statements. It's like saying A plus B equal to B plus A. Further, the axioms of axiomatic system include axiom 1, 2, and 3. Axiom 1 is alpha implies um, uh, beta implies A. Okay, and axiom 2 is this: alpha implies beta implies gamma. Whole expression implies the expression alpha implies beta implies alpha implies gamma. Axiom 3 is not alpha implies not beta, which implies beta implies alpha. And modus ponens rule of deduction, is if a hypothesis is alpha implies beta and alpha consequent means which we derive, Hypothesis means which is given. If it is given that alpha implies beta and alpha is given, then uh, beta can be derived from this statement. That is consequent. Consequent means what we can derive. Interpretation of modus ponens rule. Given that alpha implies beta and alpha are hypothesis. Hypothesis means these are the statements that are assumed to be true, and beta is inferred, that is true. As beta is also a true statement which is inferred from this alpha implies beta and alpha. All right. Example: establish that alpha implies A implies C is a deductive consequence of this statement is given. A implies B, comma B implies C. Uh, this symbol denotes that it is derived from hypothesis. This is consequent. Consequent is derived from this hypothesis. A implies C is a deductive consequence of A implies B, comma B implies C. How it is done? To understand that, let us walk through this proof of theorem. Theorem is given as whatever is there in the question, which is A implies B, comma B implies C. Deduce A implies C. This has to be proved. Hypothesis 1 is A implies B. Hypothesis 2 is B implies C. Instance of axiom 1, uh, this axiom 1. What is axiom 1? Look at axiom 1. Alpha implies beta implies alpha. So what is being done here? B implies C means this can be treated as alpha, and here this A is treated as beta and B implies C is treated as alpha. So alpha implies beta, which in turn implies alpha implies beta. So that axiom is applied here. All right. And then from this, 2 and 3. Which are 2 and 3? This is second statement. This is third statement. When you combine these two statements.
Excuse me.
Yes. Yes. Shivani?
Yeah, ma'am. Somebody are unable to join, so somebody are
Okay.
unable to join, ma'am. So that's what I'm saying.
Okay. I think now they have joined.
Okay, ma'am. Yeah.
All right.
Thank you.
MP is modus ponens. Modus ponens is what is modus ponens? This one. Uh, Given alpha implies beta and alpha. Okay. Alpha is individual statement and alpha implies beta. These are the two statements that satisfy this implies property. These are hypotheses. When these are given, from these we can derive beta. Means only beta part we can take from this hypothesis and prove that beta is true. Assume that this statement alpha implies beta is true and alpha is true, which implies beta is also true. That is modus ponens rule, MP. When you apply MP on second and third statements, what is second statement? This beta implies, no, not beta, B. B implies C. And what is third statement? B implies C implies A implies B implies C. This is third state. When you consider them, both of them, then you are getting, see, B implies C, B implies C. This when you remove means this two if you consider as alpha, then you are getting beta. What is beta? A implies beta implies B implies C. This is beta. This is obtained from statement number 2 and 3 by the application of modus ponens. Further, Axiom 2. What is axiom 2? Here it is stated that alpha implies beta implies gamma. Alpha implies to the whole of beta implies gamma. Further, the whole expression implies uh, alpha implies beta, which in turn implies the whole of alpha implies gamma. This is axiom 2. Now, when we apply that axiom 2, we obtain this. A B implies C. Uh, you just put alpha, beta, and gamma in these places, then you get that axiom 2. After you apply axiom 2 on this statement, then what is obtained? This statement 5 is obtained, on which modus ponens is applied along with the statement number 4. Both 4 and 5, when you give as input to modus ponens, this is obtained. What is this one? Beta. A imply B implies C, A implies B implies C. This is alpha. If both alpha and alpha implies beta. When you consider this statement as alpha, then what is obtained in modus ponens rule? You obtain only the beta, which is the consequent. And what are hypotheses? These two statements are hypotheses. This is A alpha, this is alpha implies beta. You obtain beta. Now modus ponens is applied further on um 4 and 5. No, sorry, 1 and 6. This 1 is alpha, A implies B, and 6 is this one. A implies B implies A implies C. If you apply modus ponens, A implies B, A implies B. Both are treated as alpha. What is beta? Beta is A implies C. It is proved that A implies C is derived from A implies B, comma B implies C through axioms and modus ponens rule. All right. Well, here it is deductive theorem. Deductive theorem says that given the sigma, which is set of hypotheses. Hypothesis, you remember hypothesis is alpha, um, and alpha implies beta. Alpha and beta are well formed formulae. If beta is proved from sigma union alpha, then according to the deduction theorem, alpha implies beta is proved from sigma. If you can prove that beta is uh, true, if it is proved from set of hypothesis union alpha, some set of hypothesis, it can be B implies C, C implies D, A implies B, A implies C, is set of hypothesis union alpha. If you can prove, then this can also be proved. Therefore, alternatively, it can be written as sigma union alpha can derive beta, which implies sigma derives alpha implies beta. Both are true. When you have sigma and alpha together deriving beta, if you just take out sigma and put alpha with beta, then it is true that from sigma you can derive alpha implies beta. That is known as deduction theorem. What is converse of deduction theorem? It is stated as given sigma implies alpha implies beta. No, sigma derives alpha implies beta. Then sigma union alpha uh, derives beta is proved. Means, here and here you can observe. Here we say that this implies this, and here we say that this implies that. Moving on to this another example. Proof not A implies implies B by deduction theorem. And what is the solution? If we can prove not A deduce or derives A implies B, then using the deduction theorem, we have proved that from this deduction theorem, we know that if it is sigma uh, derives alpha implies beta, which is like sigma union alpha derives beta. Here we have to derive this whole statement. How you can write this whole statement? You can write like a not A derives A implies B. If we can do this, it can be proved that not A implies B can be derived. And the proof is mentioned in the table. Description hypothesis 1, the theorem is this. This has to be proved. And what is hypothesis 1? Just you are taking not A, only not A part. And instance of axiom 1. Instance of axiom 1 is not A implies not B implies not A. Axiom 1, you know here, alpha implies beta implies alpha. All right. That is axiom 1. Applying modus ponens rule on 1 and 2, we get uh, just this. Not B implies not A. Because if you treat this as alpha alpha and this is beta, so alpha alpha is gone and only beta is left as a consequent in modus ponens rule. Instance of axiom 3 is here this you are putting in place of from A you got this, right? Therefore, in place of A you are putting this, and this uh, you are writing as axiom 3. What is axiom 3? It is not alpha implies not beta implies alpha implies beta. Beta implies not, alpha implies alpha, means B, A, B. And when modus ponens is applied on 3 and 4, what is obtained? Just A implies B. A implies B here is like beta, and these two are considered as alpha. This is axiomatic system. All right. Any doubts in axiomatic system? Students, if you have any doubt, you can ask. If you don't understand, you reread. Read once, uh, you will understand. If you don't, you please ask. Let us make the class interactive. All right. The third method in propositional logic is semantic tabular system. First one was natural deduction system. Second one was axiomatic system. Now the third one is semantic tabular system. What is semantic tabular system? There are two ways in which derivations can be made. First one is forward chaining. In this method, how the proof is uh, progressed. Start with the theorem, apply the rules uh, and other properties to get the derivative. Means the one which you are inferring, whatever you are inferring, that is inferred by the applications of rules from to the hypothesis. Look, it is like uh, given, you have been given with some statements. You have to infer or derive some other statement. How can you do that? From the existing statements, when you apply different rules, operators, you get uh, probably what you are looking for. Sometimes it may be true, sometimes it may be false. We learned that there is a tautology. In tautology, everything is true. Likewise, it can come out to true or false, but then in forward chaining, you begin with a proof or derivation from a given set of hypotheses or axioms. Hypothesis is given and proof or derivation has to be done. In axiomatic system, there is a need to make a guess for the selection of appropriate axiom. Which axiom to choose has to be guessed. You have to guess by looking at the statements which are given. Forward chaining is good for theoretical purposes. Its implementation in, a computer system. Uh, how can AI system make a guess about which axiom to apply and when modus ponens is to be applied? That is um, quite difficult. Therefore, other approaches have been proposed. They are semantic tabulae and resolution refutation. And these two approaches are based on the concept of backward chaining. In backward chaining, you begin with the proof or the derivative or whatever has to be inferred. With that, you start, and eventually you come to the hypothesis or the axiom. That is backward chaining. Semantic tabulae, uh, tableau. It is a binary tree which is constructed by using semantic tableau rules. If you observe, there are rules. In every system, there are rules. In NDS, there are rules. In axiomatic rules, there are rules. In even the truth table method, also there were rules. On the application of rules, we could infer something new from the existing things. Here as well, we have rules which are known as semantic tableau rules. And these semantic tableau rules are listed out in this table 4.11. Alpha and beta are two formulae. What is rule 1? Well, rule 1 says that alpha and beta is true if both alpha and beta are true. And how do you represent it in the form of a tree? You do it like alpha and beta is a root and its descendant is alpha, whose descendant is beta. And what is the explanation for this? If tabuli for a formula, alpha and beta is constructed by adding both alpha and beta to the same path. Explanation here is alpha and beta is constructed by adding both alpha and beta to the same path. Look at here, this is the same path. Rule number 2, not alpha and beta is true. When it is true, if either a not alpha or not beta is true. Therefore, here you see there are two different paths. Here they are same because both must be true. Here, if any one is true, it is true. And that is clearly shown here by two branches. The root not alpha and beta leads to um, two children. These are two nodes, child nodes of this, where one is not alpha, another is not beta. And the explanation says that a not alpha and beta is constructed by adding two new paths. Why two new paths? Because either one is true. The a whole formula is true if any one is true. Rule number 3 says alpha or beta is true if either alpha or beta is true. If alpha is true, A or B is true. I mean alpha or beta is true. Otherwise, if alpha is false and beta is true, even that situation will lead us to a true statement for alpha or beta. That's why here we have two paths, two different paths. Rule number 4 says not alpha or beta is true if both not alpha and not beta are true. Uh, Observe here carefully that wherever it is and, when both are true, it is true. This is a single path. Wherever it is or, if any one is true, it is two paths, multiple paths. Here also it's single path. Here also it's single path. Here multiple paths. Here single path. Here multiple paths. Here also multiple paths. Let us read rule 8. This is equivalence operator between alpha and beta. It is true. Then alpha and beta, or not alpha and not beta is true. Means any one of these formulae is true, then this one is true. That is shown on two different path branches. All right. Next is a semantic table for this formula has to be constructed. How it is constructed? Tabulate root is A and not B, and not B implies C. So what is rule 1? Rule 1, in rule 1, it says and means you have to write this and this separately on a single path, A and not B, and further on the same path, not B implies C. Okay, 2. And A and not B. This is also, these two formulae are joined by and. Therefore, we have A and not B on the same path. Wherever there is and symbol, you have to have the expression on the same path. When it is not B implies C. Not B implies C indicate that here not B, when you apply rule 6, not B, B is obtained, and B and not B is cancelled. So this path is closed. From where you are getting this is B and this is not B. All right. After A, you are getting not B, and after the application of not on not B, B is obtained. Therefore, both uh, gets closed. This path is closed, and this path is open. Not B, C implies C. Is this clear? This is the semantic table for this. Here, just table has to be constructed. So this is not B implies C. Not B, and here further there is nothing to go forward. Table method, for example, 4.10. Here table root is given, not A or B, and C implies B and A or C. Students, will you tell me which paths should be single and which one can be multiple? Wherever there is and, it is one single path. Here you find and, so not A or B is one formula. and C implies B is another formula, and A or C is another formula. Further, it is not A or B. A or B are A. Um, when you apply rule number 4, you are getting not A and not B, not B, A, C. Uh, Let me check rule number 4. Rule number 4 is not A or alpha or beta. It means not alpha, not beta. This one, oh, where is this one? Not A or B. This is written as not A, not B. This part is mapped to this part. Further, uh, it is A, C, A or C. This A or C have come on two different branches because of OR, and this branch has to be closed because it is A and A dash. And here C, not C and B. C and C dash, again path have to be closed. B and B dash also path has to be closed. So up to here only we can construct up to here. After this, all the paths routes are um, closed. Show that S is equals to not A or B. B implies C, A or C is consistent. How it can be shown that it is consistent? Start with this. Apply rule number 1. Rule number 1 is for and for rule number 4 is this. And rule number 3 on 4 is this. And rule number 3 when you are applying on statement number 4, you are getting here not B, A, C, this one, A or C. And here now rule number 6 is applied. 6.3. 6.3, sixth rule is alpha implies beta is true, then not alpha or beta is true. How you can write this? Alpha implies beta, not alpha, beta. Alpha implies beta means A implies B. So you can write here not B, C. When you write not B, C, if you apply this rule number 6, then only one path is closed this way and these two are open. Show that B is logical consequence of S is equals to A implies B, comma A. Start with B. Because in this it is backward chaining method. You start with the a derivative. So it is not B. Not B and premise 1. When premise 1 is applied, here you can introduce this implies A implies B. And from here we get A, and this can be written as not A, B. And here this is closed and this is closed, with which says that it is B tabuli provable from S, that is not B as root gives contradictory tabulae. Why it is giving contradictory tabulae? Because here you have not A and B not B. B not B and not A, it is contradictory and the path has to be closed. So B is a logical consequence of S. When it gives contradictory tabulae, It implies that it is a logical consequence of S. You have prove by contradiction. It is like this, proving by contradiction. All right. Next topic is resolution repetition, which we will study in tomorrow's class. Any doubts in today's class?